Welcome, everyone. Welcome to today's workshop, Tackling Climate Change with Machine Learning. I'm Kerry Colanisi, the director of the Penn Program on Regulation, and I'm really pleased to have you all here and to open up our dialogue today. The Penn Program on Regulation, or PPR, brings together more than 60 faculty from across the university. We focus on a broad range of regulatory issues, including technology and environment. And I'm really pleased that we could organize today's event, which is the first workshop in a year-long series of workshops on AI, climate change, global sustainability in an era of artificial intelligence. We couldn't put this series together without a lot of support from across the university. But at the outset, I do want to acknowledge the tireless and expert leadership of our managing director at PPR, Andy Coopersmith. Andy is instrumental in all that we do, and it has been also true for this series. And we're pleased at PPR to co-sponsor this series throughout the year with a number of other campus organizations. And I want to thank, first of all, the Provost Environmental Innovations Initiative for providing some of the financial support that makes this series possible. I also want to thank my home institution, the Penn Carey Law School, where we are very excited to have a new dean in Sophia Lee, and I thank her for her support. And in addition, we're pleased to thank co-sponsors for the Center for Technology, Innovation, and Competition, the Warren Center for Network and Data Sciences, the Wharton Climate Center, and the Kleinman Center for Energy Policy, where we are situated today and will be throughout the fall when we gather together. The Kleinman Center's remarkable staff has provided a lot of generosity in not only the space and the arrangements that we have here today, and we couldn't do this without them. I want to thank their co-directors, Mark Allen Hughes and Sonia Carley, for their support. And Sonia, if I could ask you, if you'd like to say a few words of welcome, please to come forward. Sonia Carley is new here at Penn. She's the Presidential Distinguished Professor of Energy Policy and City Planning at the Weitzman School of Design. And we're very pleased to have you here as a colleague and as part of the leadership of the Kleinman Center.
Thank you. I just wanted to take a moment to welcome you all. Welcome to the Kleinman Center. Welcome to the speaker series. Welcome to our beautiful facilities. We hope that you continue to come out for this series as well as all other events at the Kleinman Center.
Thank you very much. Speaking of those other events, we do hope you come back on October 24th for our next workshop series on climate data, where Amy Braverman from the NASA Jet Propulsion Laboratory will be here on October 24th. And then on November 20th, two of our own Penn faculty, Deep Jawala and Benjamin Lee of the Engineering School, will be speaking about toward environmentally sustainable AI. Now, this whole series of workshops has its aim to build connections in two ways. The first way is through understanding better the connections between artificial intelligence and climate change, which are two of the most consequential developments facing the world today. And you probably already agree with that, or you wouldn't be here today. But I'm a legal scholar, and over the law school, we like to drop footnotes. So I'd drop a footnote, for example, to Ian Bremmer's excellent book, The Power of Crisis. Bremmer, who is the president of the Eurasia Group, singles out as looming crises facing the world today, AI and climate change. And if not managed well, they're going to have hugely negative effects for humanity. And speaking of recent books, I don't know if you've seen Mustafa Suleyman's new book. He was the co-founder of DeepMind and writes I think somewhat ironically, the title of that book is called The Coming Wave, which is both metaphorically making the connection between climate change and technology, as we see the ravages of climate change also coming in waves. So the first connection is the connection between our AI and climate change, how AI can help solve climate change problems, improve sustainability in the years ahead, and also how we can improve AI and data analysis to be more energy efficient and less of a contributor to climate change. But there's a second way that this workshop series is about connections, and that's much closer to home. It's my hope that this workshop series will provide a venue and an opportunity for strengthening connections here at Penn between our faculty and staff and community members, whether you're working on AI or working on climate change or energy policy. We want to learn from each other, connect with each other. Penn is an extraordinary institution with extraordinary minds working on the digital sciences and working on environmental and energy issues. So it's my belief that as a society, we need to find new ways to harness these two new developments in a way that's productive. And I would be thrilled if this series helps inspire some of our students to take up pathways in your careers to use AI tools responsibly to help solve major social problems like climate change. So I'm delighted you're here, and I hope you'll join us for the other series this fall and then in the spring as well. And because this is a series about connections, I want to stop now and introduce our speaker and let you know that after his remarks, it's really open mic, and I want to encourage your participation and engagement. If you have a comment or question, just raise your hand. I'll call on you. We have staff members who will bring a microphone to you. We are recording today. It will be posted on YouTube. We want to hear what you could say and give you an opportunity to ask questions of our speaker today, who is David Rolnick, Assistant Professor and the Canadian Institute for Advanced Research AI Chair in the School of Computer Science at McGill University and the Mila-Quebec AI Institute. Maybe it's also somewhat fitting in a tragic sort of way that you're coming down from Canada, which still has 500 or so active and uncontrolled fires, an area that has burned over the course of this summer that's probably about equivalent to the area of the state of Oklahoma in the United States. And many of us here in the States have experienced the air quality issues that have resulted from those extensive fires exacerbated by climate change. Professor Rolnick is also the co-founder and chair of Climate Change AI, a nonprofit that aims to catalyze a global movement at the intersection of climate change and machine learning, bringing together, connecting researchers, engineers, investors, entrepreneurs, policymakers, industry, and NGOs. He also serves as the scientific co-director of sustainability in the digital age, which is a think tank at Concordia University. And he was named recently to MIT Technology Review's lists of 35 innovators under 35 working on machine learning and climate change. Perhaps most importantly in this audience, he was previously an NSF Mathematical Sciences postdoctoral research fellow here at Penn. So we're delighted to welcome you back to Penn to lead off our year-long workshop series on AI and climate change with a presentation on tackling climate change with machine learning. Professor Rolnick.
It's a pleasure to be here. Thank you so much for that kind introduction. Can you hear me okay? Excellent. Starting out, A show of hands. Who here is coming from some area that is related to climate or energy? Computer science or statistics or data science? Business or something related? Okay. Policy. Social sciences, not already covered. We should have more social scientists here. You're really important. Great. That is a really healthy mix. I'm very glad to have all of your communities coming here today. I'll try to have stuff that's relevant for everybody from those different communities, but please ask questions. This can absolutely be a discussion. Let's get started. I don't think the topic of climate change needs much introduction, and thank you for that very motivating example. We're seeing the effects of climate change more and more. They're becoming both more frequent and more severe. And indeed, in Canada, we see a lot of wildfires, which are both partially driven by climate change and also making it worse. As I understand it, just the fires in Quebec alone were responsible for what would normally be the annual emissions for the entire country of Canada. That said, the Canadian government doesn't actually count those emissions when looking at its Paris Agreement obligations. Policy issues there. However, it's important to remember that climate change is being felt around the world. The effects are multitudinous, and they have a disproportionate impact on disadvantaged communities and also disadvantaged geographies. Oftentimes, the countries that are hit worst by climate change are the countries that have done the least to contribute to it, and also are the least well-equipped to respond to its effects. And it's important to remember these effects are really diverse. Even if here we are thinking about wildfires, maybe somewhere else people are thinking about glacier melting or locusts or other effects of climate change that are relevant to different regions. I'm often asked, is it too late to tackle climate change? And the answer is, yeah, in some sense. Millions of people are going to die because of climate change, regardless of what we do now. And many have died already. However, we get to decide just how bad it gets. It's not an on-off switch. Actions that we take now change a catastrophe from being catastrophic to being earth-shakingly catastrophic, if you like. And so that really is, in some sense, a hopeful statement. We can make a difference. Now we need, ideally, net zero greenhouse gas emissions by 2050, according to the UN's IPCC, Intergovernmental Panel on Climate Change. We are not on track for achieving that for several reasons, which I won't get into, but we should be trying as hard as possible. Action encompasses both mitigation, which is reducing greenhouse gas emissions, and adaptation, resilience to the consequences. There's also climate science, which is sometimes put in a different bucket, which means understanding the climate and how it changes. Okay, so this is climate change. This is the problem. This is not the solution, but it's one set of things that can be used to tackle the problem. What is AI? And what is machine learning? And are they different? Well, AI is actually a really broad term and encompasses any computer algorithm that makes predictions, recommendations, or decisions on the basis of a defined set of objectives. That's the official OECD AI definition. Paraphrase a little. That's really broad. You'll notice that it encompasses a lot of things and many things that we wouldn't consider to be intelligent. Arguably, there is no system out there that we should be considering to be truly intelligent. But there are a lot of algorithms in there that are very specialized for particular purposes. And that's actually most of what we're going to be talking about today. For all that AI in the news right now is probably all ChatGPT and maybe some self-driving cars, that is not actually the kind of AI that we're talking about, and not the kind of AI that's most relevant for tackling climate change. Machine learning is a subset of AI, and it is concerned with AI algorithms that infer patterns from data. Rather than being told explicitly how to solve a problem, the machine learning approach is to look at a lot of data, infer patterns, and then extrapolate those patterns to new data that is unseen, and then use that system to try to solve the problem in the new data. This has become extremely popular and effective recently, thanks to deep learning, which is also called neural networks. And so machine learning is, generally speaking, being used in anything that you see in being talked about as AI now, but that's not completely true. Now, there are strengths and weaknesses of machine learning and AI more broadly. Machine learning, in particular, is very good at performing straightforward tasks quickly and automatically. Not tasks that necessarily require a high degree of intelligence, but labeling images, for example, which a human might not want to go through repetitively. Scaling that up with machine learning is a great idea. Finding subtle patterns in large data sets, and that's essentially what machine learning is doing all the time. Finding subtle patterns that a human might not have the patience to find is really valuable. And optimizing complex systems. Maybe you have a big system with many knobs that can be turned, and you'd like to optimize it in a particular way for a particular objective. That's a good use for machine learning as well. Weaknesses. It's very sensitive to the data, not surprisingly, given that it relies upon generally large amounts of data. So if you have smaller data, or if the data is bad or biased, maybe it's biased because it comes from certain geographies, maybe it's biased because it comes from people, and people are biased, then you can end up with bad or biased conclusions. And sometimes that's particularly bad because it has the veneer of objectivity coming from an AI algorithm. The AI algorithm says it's true, but actually it's just a problem in the data. It can't think outside the box. This is really difficult to conceptualize sometimes when we have an algorithm that seems like it's doing all kinds of intelligent thinking, but it's really just performing the task that it was designed to do. This is the case for everything from very specialized algorithms for playing a game to where, for example, if you have an algorithm that's designed to play a video game and you change the background color, the algorithm no longer works because it cannot generalize and think conceptually the way that a human can. That's also the case for ChatGPT, which is able to regurgitate information that's seen and parse it in really new and impressive and useful ways, but not actually come up with definitively new insights because it hasn't got a model of the world in it. It hasn't got a mind. So those are some of the weaknesses. And then generally, you can't also explain the reasoning behind how an AI algorithm works. Generally, it says this is the answer, and maybe it is the answer, but it's hard to get from the algorithm exactly how that answer was derived. With all of those strengths and weaknesses in mind, how are the two things related? How is climate change and climate action relevant to machine learning? I'm first going to be talking through an overview paper called Tackling Climate Change with Machine Learning, which we wrote to provide a comprehensive analysis of the different ways machine learning can be used in helping tackle the climate crisis. If you're interested, I highly recommend you check out the full paper. It's 100 pages, so I'm not going to be going through all of it, but maybe there are particular ways that you would, particular sectors that you're interested in, or particular technologies. There's also an interactive version online where you can search by theme. But I do want to touch on some of the overall themes that we see in how machine learning is relevant in addressing the climate crisis. The first one is improving operational efficiency. For example, there are many systems that are highly energy intensive and necessary across society that are automated and have the ability to be controlled in automated ways. Machine learning, since it is good at turning knobs to control something very efficiently, can be very useful in such cases. For example, in HVAC systems, heating and cooling systems used in buildings, everything from smart thermostats used in a personal house to controlling the heating and cooling in a big industrial or commercial building. Steel and cement manufacture, which together contribute about 15% of global greenhouse gas emissions, which is a huge number. Those industries are considered difficult to decarbonize, and there are ways to optimize those processes using machine learning to make them use even just a little bit less energy or a little bit less emissions can make a huge difference just given the scale of the operations. Gathering information. Oftentimes, there is a big data set out there, unstructured data that needs to be turned into useful information, for example, to guide policy or to guide other forms of action. And machine learning can be good at parsing that data and providing insights at scale. For example, in taking satellite imagery to estimate carbon stock, how much carbon is stored in a forest or a grassland or a peatland. Or parsing financial disclosures, taking a big document and picking out useful pieces. By the way, you probably still don't want to use GPT for that. It's a bit closer to being relevant, but they're actually better specialized algorithms in that particular case. I bring up GPT because outside of academia, often in the private sector right now, everybody's so excited about GPT. A bit tiring. Forecasting. Oftentimes there's data in time series is the technical term, so time points, and you'd like to see what's going to happen next, maybe with auxiliary information that can help you make that decision. For example, you want to balance the electrical grid and not overproduce electricity. So you might want to predict how much electricity is going to be produced at any given point in time, especially important if you rely on solar and wind, where the amount of power available changes as the sun shines and the wind changes. Or you might be interested in predicting demand, because that also varies from moment to moment. The UK's National Grid, for example, recently instituted a new AI algorithm which predicted demand and cut their error rate in half. That's the kind of savings that you can sometimes get in these kinds of applications. Speeding up simulations is the fourth theme. There are many settings in climate change where there is some complex, often physics-based process which needs to be simulated. And in order to do that, we throw a huge amount of computation and effort at the problem in order to simulate the physics. Climate models, for example, can take months to run, even on supercomputers. And so there is a huge need for making these things run faster and more scalably. If for no other reason than that this is impractically slow. And also we can run more of them if they are fast. Same thing with electrical grid planning models. In both of these cases, AI and machine learning are increasingly being used as fast approximations to the simulation. They're not better than the physics, they're actually worse than the physics. We understand the physics of the climate very well. But if AI algorithms are fast approximations, then they can help us scale up this simulation process. And then finally, there's the process of accelerating scientific discovery. We need a lot of innovation in climate tech very fast. And AI is not going to solve that problem for us, but in certain specific cases, it can make suggestions of things that we should try from an experimental perspective. It's not replacing experimentation, but it is speeding up the innovation process. Now, supposedly, Edison's team tried thousands of materials for a light bulb before settling on one that worked well. Hopefully, with specialized algorithms, we can speed up that iteration process so we don't have to try thousands of new materials for photovoltaics, solar perovskites, for carbon capture sorbents, and other useful materials. Okay, so let's dive into more detail on these 5 different themes, with an example of each one from our own group at McGill and Mila. Efficient operation of power grids is a major problem faced by power grid operators. Technically, there is this thing called AC optimal power flow, and it looks like that, mathematically speaking, on the right-hand side. This is a non-convex optimization problem, which for the computer scientists in the room, you will know that means it's hard. It is hard to solve a non-convex optimization problem exactly, and so in practice, people simplify this problem. They linearize it, which means that they can solve it fast, but it means that they're solving the wrong problem. That translates into wasted power, especially in the situation of solar and wind power, where you have to solve this problem more and more times because the parameters are changing. There is a need for fast solutions to non-convex optimization problems, in particular this one. Now, naive AI algorithms can approximately solve this problem, but you end up trading off between optimizing for your objective, which is reducing the amount of overall power, reducing the cost of the power being produced. You're trading off between that and satisfying the constraints of the electrical grid, power grid, the power flow constraints. In practice, that means that you almost perfectly optimize your objective, and you almost perfectly satisfy the constraints, and so you almost satisfy the physics of the power grid, which means the power grid still breaks and you get a blackout. Almost satisfying the physics of an engineered system is not good enough. You have to exactly satisfy the physics, or else your engineered system will break. So we need a system that can approximately solve this problem while ensuring feasibility so that there are no blackouts. I'm not going to go into the details of this, but we have a deep learning algorithm that can approximately solve non-convex optimization problems. 10 to 100 times faster than traditional methods without violating power flow. So it can actually be used by the power system operators. Next application that I want to touch. This will be less technical. So if you didn't like all that non-convex optimization stuff, tune back in. Gathering information on ecosystems. Ecosystems are collapsing, but evaluating biodiversity requires specialized experts. Now, ecosystem collapse and the biodiversity crisis is not the same as the climate crisis. There are many factors at play, but climate change is a major one. AI can help scale up ecological monitoring. We don't have enough people on the ground to gather all this data, so we can benefit from new technologies. There are many ways in which we are working on this. First one, we're developing automated sensors to monitor insects. With collaborators across many different countries, our systems are now deployed across North America, South America, and Europe. These are what the sensors look like. We're working on the software side. That's the hardware side. This hardware device tracks and photographs insects, and our software systems identify them. We're currently focusing on moths, which represent actually 10% of all species, including plants and bacteria, are moths, which is incredible. And then the data are sent to ecologists for interpretation, proofreading. This enables you to go out into a remote location and get a snapshot of the full biodiversity of 10% of the species at that given location. And you can put this out for months and then collect the data at the end of the year. This is what it looks like. Identification of individual species attracted to the device with confidences there. We also track how many there are and how long they stay and various other properties. The goal is not to replace the entomologists who are actually studying these moths, to be clear. The goal is to give them more data because the biodiversity experts always need more data. Second project, instead of going down to the ground, we can zoom out. And the problem that we're trying to address here is that there's imbalanced data on different places and different taxonomic groups. If you are trying to monitor a remote location far from people, or if you're trying to monitor taxonomic groups which are very understudied, like beetles, nobody really cares about beetles, unfortunately. We should, they're a quarter of all species. But how do you do that? Well, we're using satellite imagery to help fill in the gaps. Estimating ecosystem properties and estimating biodiversity on the ground using satellite imagery. We can take an image like that and predict what species, currently working with birds, are going to be found in every particular part of that. Those pinpoints are actually showing the locations of a species called the bobolink, which specializes in meadows of a certain age. It's not just meadows, it's meadows of a particular kind. And we can estimate that. This is a rare species which needs to be protected. And understanding those kinds of properties at scale can really inform land use decisions. Another project, which I'll touch on really briefly, we're inferring tree species, crown size, other properties related to carbon stock from satellite and drone imagery in collaboration with plant biologists. And this is like large-scale forest monitoring across Quebec. Final thing I want to touch on here, we just were announced as the winners of the Global Centers in Climate Change and Clean Energy competition. We are now running the Canadian side of one of 7 global centers in climate change and clean energy, focused on AI and biodiversity. So stay tuned for more details on that. Also, if folks in the room are looking for postdocs, we have a call for postdocs open in this. Forecasting, a quick example of that. Forecasting crop yield is really essential to averting food insecurity. Changing climate and weather patterns means that crop yields are varying and potentially at risk across the world. AI and machine learning can help predict crop yield from satellite imagery, but data is, as in many cases, the bottleneck. Not the satellite imagery, there's lots of satellite imagery, but labels to develop the AI algorithms, what's called training them. How you actually create the AI algorithm, how you design the AI algorithm, you need some labels. You need to know where the crops are and what the yield is. And that data is scarce and it's uneven across different locations. In the map at the bottom, which was created by our partners at NASA Harvest, you can see these orange dots, which are the only places where we know in this data set what type of crop is there. The blue dots are, we know if there is a crop. The orange dots are the good data, and you can see they're very sparse. They're not in most locations around the world. So in work with NASA Harvest, we developed meta-learning algorithms for crop yield prediction that can quickly adapt to new locations and crops. Suppose that you have, for example, seen coffee in Kenya and maize in Brazil, then you can work out what coffee in Kenya looks like without having seen it. What's called zero-shot learning. This ability to generalize can vastly improve geographic equity and just the performance of these algorithms across different settings. These methods have actually also proven effective in very different settings, like optimizing HVAC systems in buildings, so again, heating and cooling systems in buildings, and monitoring carbon flux. These are completely different problems, but oftentimes really thinking about what's needed in a problem and what the stakeholder needs are for that problem. In this case, recognizing that geographic equity is a major hurdle to current algorithms. Thinking about those problems, you can end up addressing a whole range of seemingly unrelated problems sometimes. Speeding up simulations. Climate simulations, as I mentioned, are accurate, but can be slow. This can make it harder, in particular, to get localized predictions that help in adapting to climate change. For example, the city of Phoenix is warming much more significantly than the surrounding area. If you were the mayor of Phoenix, you would want to know that and know how it is happening in order to better prepare. However, climate models currently are so slow that they have to be run at resolution of hundreds of kilometers. There are several ways to go about addressing this problem. First thing, we use AI to quickly approximate radiative transfer computations. This is an especially slow part of standard climate models. The algorithms leverage some known physics, incorporating that physics into the design of the machine learning system. We're currently working with Environment and Climate Change Canada, which is the Canadian agency responsible for climate and weather modeling, to integrate that into our official climate model on a national scale. Another approach is to do super resolution, which is taking an image that's at low resolution and making it high resolution. Sounds like magic, and you can't do it you can't do it perfectly, but there are ways that AI algorithms have been developed to perform super resolution very effectively. You can take that blurry image, I think that's atmospheric moisture content, and make it high resolution. So we have improved the AI methods for what's called downscaling or super resolution in the climate context, so that they do two things. First of all, respect physics-based laws like conservation of mass, energy, etc., and that they can actually predict arbitrarily high resolution, leveraging what's called Fourier neural operators. And if you're interested in the details on that, I can talk to you about that. So that means that we can take a blurry image and we can double the resolution. We can actually then quadruple the resolution. We can increase the resolution as much as we want. It's not going to be perfect, but it's going to be able to do this, to solve this problem to a reasonable degree of accuracy, and better than any prior algorithms. And in the third project, we're actually working on incorporating an element that's often lacking in AI. I mentioned that it's really difficult to get explanations for why something is true from an AI algorithm. However, there are approaches just being developed to work on this, and here we are trying to link causal relationships between input variables to understand not just how the climate, not just be able to predict what the climate is going to do, but actually identify new causal drivers within it, including what's called teleconnections, which are far, far apart parts of the climate system that seem to influence each other. The final example I wanted to touch on is accelerated discovery of new catalysts. So the energy transition requires efficient electrocatalysts, which are catalysts that make a reaction happen faster when you add electricity. For example, introducing green hydrogen or electrofuels. These are very important. And finding new catalysts requires currently slow quantum chemistry simulations. And there are many possibilities to choose from as well. There are many possible catalysts, and evaluating any particular one takes a long time. Both problems. So we're developing AI methods to address both of these, quickly evaluating candidate catalysts. We already have a couple of papers down there you can see, and suggesting promising candidates that you should try. This is not a replacement for experimentation, but a way to reduce the number of experiments to try. some key considerations in thinking about the applications of machine learning in a climate context. First of all, it's not a silver bullet. AI and machine learning are not magically going to solve climate change. They're not even magically going to solve any one of these problems. They are one piece of the puzzle. They're only relevant sometimes as well. There are many problems in climate action where AI is just completely irrelevant and you shouldn't be thinking about it. High impact applications are also not always flashy. The applications of AI that you read about in the news are probably not the ones that are having the biggest impact on the climate or on society at large. Self-driving cars, for example, are probably actually going to make climate change worse. By contrast, even in the transportation sector, there are great applications of AI from a climate perspective. For example, predictive maintenance of railroads. You don't read about that in the news. It's not really flashy, but Deutsche Bahn, the German railway operator, has made the system of railroads in Germany much, much more efficient by finding failures with AI. Interdisciplinary collaboration. These kinds of problems are not going to be solved by either AI people thinking, oh, we can magically solve everybody else's problems, which happens so often. Never listen to the tech industry when they say that. It's also not going to be solved by people who don't understand AI, using AI to solve their problems. Generally, that fails too, though it fails less badly. If you don't know anything about AI, it's kind of easier to spin up an easy AI algorithm. But it's necessary at every stage. First of all, scoping the right problems. So you're working on a problem that's actually relevant. I can't tell you how many times somebody in computer science said, oh, I'm going to solve this major climate change problem of like, why aren't people having enough indoor plants? That was actually something that got pitched to me at one point. That's not going to solve climate change. And in many cases, you need to understand a lot about the problem in order to understand how you should create your solution. So building relevant domain information into your solution is really important, or else you are missing part of what you can use to help solve the problem. And then shaping pathways to impact. Understanding that your innovation doesn't end when you publish a paper or release a cool demo, it actually has to be scaled. And collaboration with people across sectors is really important. The other lens that I want to bring up is equity considerations. The field of AI is not known for being strikingly diverse. And I say this as like a white cishet guy at one of the traditionally powerful AI institutions. We have huge problems here. And these problems are compounded when we're considering a topic like climate change, where issues of climate equity and climate justice are fundamental to understanding how climate change impacts society and also how our solutions need to be developed and deployed. Understanding and empowering diverse stakeholders in AI and climate change is paramount. Understanding the implicit selection and prioritization of problems is also important. Understanding that, for example, there is a lot, as I mentioned, of attention given to fires here. That's great. Fires are an important problem to be solving with regard to climate change. I wish there were as much VC funding for locusts, which affect East Africa, the Middle East, and India, but don't affect North America. Silicon Valley has a lot of fires. It's not coincidental that Silicon Valley spends a lot on addressing wildfires. Locusts are made worse by climate change, but there are no locusts in North America. We made them extinct about 100 years ago. Ensuring data is representative as well. Machine learning algorithms rely on data. If all of your data is drawn from one geography, your algorithm is only going to be relevant to that geography. The opposite problem, if you're gathering data, think about where you're gathering it from. Sometimes there's data colonialism where data is taken from places that have low data regulation. Maybe the EU has too much regulation, and so you go to a country in the global south where you can just take people's private data. That's also a problem, both extremes. Okay. I want to touch also on challenges for machine learning for those computer scientists in the room or people interested in machine learning and computer science culture. There are several challenges in climate relevant applications, which are really key machine learning research challenges and make problems more exciting for those of us in computer science. There are constraints on variables, for example, those drawn from problems drawn from physics and engineering, which need to be satisfied, as I mentioned in the context of electrical grid optimization. That's really hard to do with current AI algorithms. Distribution shift. So your data might change across geographies or time. The nature of the data might change. That's really tough to tackle. Limited or imbalanced data. Often data is very expensive to collect, or at least labeled data. And interpretability or accessibility for end users. These are all challenges that you encounter in climate relevant problems that raise really interesting research conundrums for computer science. And these challenges often take problem-specific forms. This goes against the culture of machine learning, which is often data-driven and problem-agnostic. Using high-powered machine learning techniques naively often fails in these contexts, or it's overkill, but it often fails because you need to consider the problem-specific constraints and the problem-specific information. Just throwing more data at a higher powered algorithm of a problem is generally not the way to solve a climate change relevant problem. The machine learning community needs a culture shift if we're going to actually tackle societally important problems. And there's innovation needed in structures for incorporating domain information rather than just trying to learn everything from data. To give an example of how the implicit design of machine learning tools is not geared towards societal impact, let's take a look at ImageNet. Machine learning continues to rely on benchmarks, like these big data sets where you can compare your performance to other algorithms. And they're used for both evaluating models and pre-training for applied settings. So you start, you develop your algorithm on ImageNet, and then you tweak it a bit based upon whatever your final task is. These benchmarks are generally derived from internet data, and they're generally derived also by computer scientists. There may be a problem if everything is built from the internet, which is not known for being a very healthy place, and is designed by computer scientists who are not known for knowing everything about society. We worked with ecologists to understand ImageNet, which is actually a quarter wild animals, and we found that a significant fraction of the images are just flat out wrong, which is impressive given that if you get a 0.5% increase in performance on ImageNet, you can publish in the top venue and you'll shout it from the rooftops because that kind of accuracy increase is unheard of. But why is that accuracy meaningful if 12% of the data is wrong? And 12% of the categories are also contradictory. In addition to that 12%, there's another 12% of the data that's wrong, 12%. These are two separate 12%. There are huge biases too. And going into a bit of this, the species are heavily biased towards the US. For example, those are 4 species of jay in the category J. The one on the top left is the one that you probably see around campus. It's the blue jay, but it's actually only found in the US and Canada. There are 49 species of jays around the world. And despite that, 2/3 of the data in the data set is actually just the blue jay. Most of the jays don't have any images at all. So if you're trying to create a solution for China, where this is the Sichuan jay in the bottom right, or Mexico, where there's the green jay in the top right, you're out of luck. This is exemplary of machine learning innovations developed without stakeholders relevant to societal impact. No ecologists were consulted in creating ImageNet, and yet ImageNet is used in ecology applications now. This is really problematic. I also want to touch on how AI can negatively impact the climate. There are several ways. Probably the first thing that jumps to mind is computation-related impacts. There is energy required to use a computer and to use AI algorithms. There's sometimes a lot. There's also embodied emissions from hardware. To create a server, you need to also, you need to spend a lot of energy. You need to extract some heavy metals. There's water extraction as well. And so there are lots of emissions there. In practice, this is actually really low for most AI algorithms because most AI algorithms aren't the big ones that you read about in the news as being, energy hungry. Like GPT is really energy hungry. But the algorithms that I talked about today, those are all really lightweight. They could probably run on a laptop. It really varies. This is sometimes an important problem. It's particularly an important problem for these large language models. But actually, this is just the tip of the iceberg. There are so many other ways that AI is making climate change worse. Isn't that great? Good to know. The problem is even worse. So in particular, I want to highlight the applications of AI in fossil fuel extraction and exploration. They are estimated to yield a 5% production boost in certain cases, and to have contributed to $500 billion in additional profit for the oil and gas industry just by 2025. That's how big AI in oil and gas extraction and exploration is. So adding these nice applications of AI, there is this elephant in the room. And would you believe it, there's probably an even bigger elephant in the room. Systemic impacts of applications, not just direct impacts, AI-enabled advertising systems, which are designed to increase consumption. We don't have any idea about the scope of these impacts, but all of online advertising is now built on AI. So when we're thinking about how AI is impacting the climate in negative ways, these just get bigger and bigger, less well quantified, but bigger and bigger. And it's important to remember that these can be shaped. And I'll take the example of autonomous vehicles as an example here. In autonomous vehicle technology, self-driving technology, most of the attention is being given to cars, personal vehicles. But we could be doing that with buses. Implicitly, the technologists are driving the priorities based upon existing paradigms of personal vehicle ownership, which means that we are reinforcing those paradigms. We're also making it easier for people to drive, and it's expected that self-driving personal vehicles, cars, will make climate change worse for that reason. But if we were building self-driving buses with all of that energy, that would be making climate change better. So the implicit choices that we make in developing a technology really matter. I'm not saying we should go out and ban some use of an algorithm, but we can shape the incentive structures and we can shape the decisions that we make. And computer scientists saying, oh, somebody's going to use it for this, it's not my business, that is making the problem worse. We need to think of AI for good, which is this horrible term. It doesn't mean just adding new good applications of AI on top of business as usual. It means shaping all applications of AI to be better for society. Now, drawing to a close for the policy people in the room, I want to quickly touch on some of our policy recommendations. So this is a report for the OECD's Global Partnership on AI, which is the body which coordinates national AI strategies. And we produced another 100-page report. This is recommendations for government action, how governments can better shape the uses of AI in the context of climate action. And here are some of the areas that we considered, everything from data and digital infrastructure through funding systems and capacity building. Here are some of the selected policy recommendations. Improving data standards and data sharing. Oftentimes, data is the bottleneck, not the only bottleneck, but sometimes that is a key bottleneck, limiting solutions in this space. The data either doesn't exist or it exists across lots of dispersed places, and there aren't ways to coordinate that or actually use it. Data task forces and platforms can help address this problem. Impact-driven funding. Often AI funding is driven by what is cool and new and is solving these benchmark data sets, not actually helping society. Thinking about impact-driven funding. Cross-sectoral innovation centers, because oftentimes innovation is not guided by deployment. It's guided by, again, these separate benchmarks and notions of innovation divorced from societal impact. And bringing private and public stakeholders into the room to shape innovation is really important. Building AI capacity and literacy. If nobody in a sector or in a public or a government body has any knowledge of AI, they're not going to understand where it is and is not relevant or how to actually use it. Upskilling programs are really important, so training people from the relevant from the relevant body in AI, and secondment programs, so bringing people from AI into the relevant body. Both are important. Establishing best practices for, in particular, participatory design, understanding that we should be designing these systems with stakeholder needs in mind, and then considering holistically the potential climate impact, not just of applications of AI that are, explicitly geared towards climate action, but also all applications of AI, because recommender systems for advertising are strongly impacting AI. In closing, I want to point you to some more resources. If you're interested in learning more about this space, the nonprofit that I co-founded, Climate Change AI, has a lot of resources, including those reports for researchers, practitioners, policymakers. We have a workshop series. So if you want to go to a physical event, our next one will be in New Orleans at NeurIPS 2023. You can also see all the past papers from that on our website. There are about 600 of them right now. We have a summer school, which had 10,000 people this last year from 165 countries. That's the virtual part of it. We also have an in-person part, which is more competitive. That welcomes people from all backgrounds. We have funding programs. We've given away about $3.5 million so far in grants. We have a newsletter. If you sign up for a single thing, I would recommend the newsletter because it gives you monthly updates on what's going on in this space. everything from jobs to new papers and new announcements. And we also have things like webinars, happy hours, a lot more. And then my final closing is to thank everybody in my lab who contributed to all of these papers that I talked about. I also should thank the Climate Change AI team who contributed to the Tackling Climate Change with Machine Learning paper in the GPA report. But our lab at McGill and Mila, all of that work would not be possible without all these people. And also we are recruiting new postdocs and interns and potentially new graduate students. So reach out to me by email if you're interested in those opportunities. Looking forward to the discussion. Thank you so much.
Great. Thank you very much. Okay, we have time for questions, and I would encourage you to raise your hand and we'll bring some microphones to you. I want to ask one question at the outset, and it builds on one of your latter slides, the recommendation for impact assessment. Can you talk about how you get to ground truth to know that what you've trained the algorithm on and how it's actually being applied is indeed leading to something that's more optimal, more accurate, less biased, or whatever?
It's going to depend on the use case, and there are going to be different metrics for success. Your metrics for success might be the amount of adoption. There might be reduction in greenhouse gas emissions for a particular use case, but that's oftentimes difficult to measure. You have to sometimes be okay with ballpark estimates, recognizing that sometimes getting an exact number is actually confusing in the sense that sometimes the exact numbers only capture a small fraction of the story, right? So sometimes knowing whether something is high impact, medium impact, low impact, or the order of magnitude is better than trying to get an exact number that's going to be assuredly wrong. There might be metrics associated with equity, with robustness under different circumstances, with privacy or security. Different settings are going to have different metrics for success. And so recognizing that oftentimes the standard machine learning metrics of accuracy, or how do you decrease your loss function, technically speaking, those metrics for success are often not the correct metrics in this kind of context. Does that begin to answer your question?
So you would do additional sampling and evaluation through more conventional statistical techniques.
Let us
sometimes at least.
Let us take an example.
Yeah.
In the case of moth monitoring, insect monitoring, we have found that our systems have already been used to identify about 100 new species, new to science. And that was just in a week. We're actually going down to the particular research center in Panama where we found those species and really doing an in-depth study. So that would be one measure, but that's just new species, new to science. We've had many thousands of observations from across the world being fed into scientific databases as a result of these systems. So that's, in some sense, the metric for success. How much data, in this case, is being created to feed into conservation and land use decisions. In another setting, it might be adoption by power grid operators and how much of a boost in efficiency you got as a result of that.
Okay, our host will give you the first question.
Thank you for the excellent presentation. So my question actually builds on yours, and that is, I want to call it truth creep. How do you ensure that over time we don't get farther and farther away from truth? With each, so let's say you have several AI mechanisms happening today, and each one has a little bit of error to it, right? Because yes, logically they're not going to be perfect. But then tomorrow we have a whole bunch more, and they're pulling from both reality, other data, as well as what you generated yesterday.
Pulling from an AI system. You should never be pulling your data from an AI system at all, or using an AI to evaluate another AI. There are rare exceptions, but generally speaking, maybe that's addressing your question. Yeah. Yes, you need hand-labeled data, or there's some notion of ground truth. That is always the gold standard in machine learning. increasingly, we're seeing really scary scientific methodology that is using AI to grade itself. And we might as well just throw up our hands and give up on science if that's what we're doing.
But what about Chat GPT, right? So let's say a whole bunch of students write a paper and submit it into a class, right?
Yeah.
And then those papers live. And then the next class period, they might scour the internet through the same process, write a new paper that's pulling from the papers that might have had error in it in the past.
Trusted sources. You shouldn't use as a source a random paper that you find on the internet. It's also why, honestly, ChatGPT shouldn't have been developed to just pull random sources on the internet. This is an unethical and frankly illegal way that these tools are being developed. It's processing in the courts, but this kind of use of people's private data is not okay. But in how do you avert this in these climate applications? We're not just pulling random data sources off of the internet. We're pulling, gold standard data from power system operators or from ecologists. And there isn't really a way to fake that. It can be wrong in some sense, but it's not going to be wrong because it was covertly generated by an AI. There are these difficult situations where you're running a system with an automated controller. And how do you phase in a different automated controller? And there is this notion of self-play where you can try to improve against an existing algorithm, but that's because you have a metric for success, which is external to the AI algorithm. That's because your metric for success is maybe the amount of energy that you're using. If you control the system to use less energy, there's no way to fake that. There's just less energy being used. So in some sense, the way in which you get there doesn't matter as much. Does that help?
Okay, we'll go to the back.
Yeah, don't pull essay sources just randomly from the internet. It was never a good idea, and it's still not a good idea.
Hi, so I'm coming here as an ecologist who doesn't have much of a background at all in really anything tech. So can you talk more about ways that AI can be used either in conjunction with ecologists to solve sort of those problems?
Yeah, so we work on a lot of different biodiversity monitoring technologies, and there are many different modalities that AI is being used in this space. The main modalities include, well, the technology for a lot of these applications is computer vision, which is just looking at images using AI or other algorithms. And that can be used with citizen science data, so people taking photos of species themselves. It can also be used with camera traps. It can be used with remote sensing. But it's more than just computer vision. There's increasingly a lot of AI being used in acoustic monitoring. So to process, say, there's the fantastic app Merlin, if anybody's using that for identifying birds, that's great. We have that for other species, other taxa as well now. Increasingly, those tools are being used at scale. eDNA is also a valuable data source, which is also being processed by AI algorithms. I encourage you to check out, for example, the BioScan project, where there's a huge initiative on scaling up eDNA, so environmental DNA sequencing, and monitoring using AI. Other data sources include like processing citizen science data or large-scale data to create SDMs, species distribution models, and inferring this kind of system-level property from individual observational data points. What am I missing here? There are other sensor systems. There's like the sensors that you actually just physically place on an animal. That's relatively rarely used now in AI-based monitoring. I think those are the main ones. I'm thinking the main ones. But there are nice review papers. I encourage you to check out the work of my collaborator, Sarah Beery, for example, for some of these overviews of AI and biodiversity and ecology.
And on that last point, by the way, we will, at the website for the AI and climate change workshop series, be adding a resource page. So we'll take these suggestions of papers and websites and so forth, and we'll be populating it there, obviously linking to all the resources that you have as well. So be sure to check that out. Let's turn to up in the front.
My question was largely answered in the tail end of your response. It was about biodiversity SDM stuff. So if you'd like to speak a little bit more to that, I'd appreciate it. But then also I'm interested in the kind of urban scale climate impact modeling space. And so if you could speak to applications of AI within that space, that would be of interest too.
Yeah, absolutely. So first to your question about SDM. So species distribution models refer to understanding the distribution of species over given areas. And there are different sort of standard statistical methodologies that people use to create SDMs using ecological data. Please, ecologists in the room, hold me to account if I'm saying anything that's incorrect. So the ways in which my own group has approached SDM inference is, as I mentioned, with remote sensing data, where we're taking citizen science data as ground truth. We're using remote sensing data to predict citizen science observations on the ground. We're working with presence-absence data, which is relatively rare in citizen science contexts. We understand both where species are and where they are not. And this means that we can actually predict the encounter rate for a species using satellite imagery, so how often you're going to run into it on the ground. There are other ways that people are working with SDMs and AI, various forms of interpolation of observations. Maybe, for example, a species is found across this entire area, but there are no people there to see it. For example, if you look at any database of observations of species, you're never going to see any species in basically the entirety of Central Africa. And this is because there are huge areas where there just aren't a lot of people. They're concentrated, generally speaking, in cities, like in most places. But also because these platforms have really poor reach. They were started generally in the global north, and they don't actually interface with the people on the ground in Central Africa who are out there looking at nature. And for both of these reasons, you don't get observations, but clearly the Central African rainforest is not exactly devoid of species. So how do you interpolate across these kinds of regions? Well, AI can help you do that, and there are algorithms in particular that there is a team led by Asheen McKay at Edinburgh that I would point you to if you're interested in that. With respect to adaptation in cities, sorry, I realized I forgot to get to that. Some people have worked on urban heat islands and simulation of like airflow in cities using AI. There's a lot in the health space, so that's not all AI, obviously. There's just a lot of data modeling. I would point to a lot of extreme event work. In particular, coastal inundation is a problem that's been assessed pretty extensively using AI. Coastal inundation means like flooding along a coast. That's a problem both because it's interesting. Extreme events are getting more frequent and more severe. There are bigger storms. There are more frequent storms in some places. It's also the case that the sea is literally expanding because a large fraction of the heat that we produced has been absorbed by the sea, and seawater expands very, very slightly. So the sea level is rising from that, and of course, it's also rising from melting glaciers. So for all of these reasons, coastal inundation is a problem. People have used AI to exactly map the elevation of particular parts of cities and found that hundreds of millions of more people than had previously been supposed are actually at risk from coastal inundation. Not good, but it's useful to have that kind of information.
Okay, over here, the purple shirt.
First off, thank you so much for your talk. Second, this question is pretty particular to like simulation and research, and maybe it's something that you'd refer to these reports to read to answer. But as someone who has a climate research question that I'm trying to use machine learning to solve, how would you go about evaluating what type of algorithm to use? And if your data is bad and questions like that, what's your process kind of?
Well, start with the simplest possible algorithm. You should never start with a complex algorithm when a simple one might do the job. Start with like regression, random forests, XGBoost, various different relatively simple approaches. If you want to use deep learning, absolutely, but try simple things like a UNet or a multi-layer perceptron or something like this, depending on your circumstances. Obviously, look at the literature to see what people have tried in the past. Oftentimes, these simple approaches will work really well. it's generally a good idea if you are coming from not an AI background to collaborate with somebody who has an AI background to make sure you're not doing something really bad. In particular, a common mistake is to validate your algorithm on the data used to train it in some fashion. And there are lots of ways that you could be secretly doing this that you aren't aware of. So watch out for that. In particular, geographical autocorrelation is a really big one. Don't pick your testing data points to be right next to your training data points because they're generally really similar. So that's one big, that's a one big mistake. But I would say overall, talking to some people in a complementary area is generally a good idea. They will, if you talk to computer scientists, they'll generally say, oh, there was this latest paper with some cool vision transformer, and maybe you want to use that. And maybe you do, but probably you want to use half a dozen simpler things first.
Okay. On this side, the gentleman with the white shirt, blue jacket.
Thanks. Thank you so much for your time. So I wanted to ask, you touched on a lot of very interesting projects. If you had to pick one that was the most important or most impactful, particularly from like a commercialization perspective, perhaps to solve climate change. I ask because I'm coming from a sort of business background and I want to be able to think about where I should put my effort.
Absolutely. So I generally avoid answering this question because it's not about a single most impactful problem or solution. It's about a single most impactful problem or solution for you. And I would think in terms of what your personal skills and background and interests are. So if you have, for example, existing partnerships or knowledge in a certain space, I would look at that space and think about how you can make an impact there. Now, if you go to Climate Change AI, which is up there, if you go to climatechange.ai/summaries, you can get the summaries version of the big compendium paper, and you can search by topic area, and you can find particularly high leverage examples. That's not going to completely answer your question, but if you say, I'm interested in the transportation sector, you can find high leverage problems in transportation. And that would be how I would suggest going about it, probably. But recognizing that it's about a fit between you and the problems. There is no one super high impact application. There are a lot of medium impact applications.
Okay, in the front here. We'll get you a microphone so this can be picked up on the
You can have 2 mics.
recording. You can have your choice.
Thank you so much for your talk. So one of the policy recommendations that you outlined, I appreciate that you had a bunch, but one of them was to develop innovation centers.
Yes. Sorry, I'm just seeing if I can move the slide step. Yes, innovation centers.
Yes. So are there any at the moment that are incubating projects and facilitating collaboration that you could speak of?
Yeah, to a greater or lesser degree. There are projects within existing centers, like the AI initiative within EPRI, the Electric Power Research Institute. That is really valuable. I'm glad that that exists. We need to have more of those. There are this is what we tried to build in this new global center in AI for biodiversity change. It is multi-sectoral in that it includes both ecologists and AI experts. And in that particular case, the relevant stakeholders happen to be much more within the research communities. So generally speaking, it should include private sector as well. And there is some amount of this. There are some amount of tailored incubators. So for example, like Cyclotron Road is relevant. Some of their stuff is relevant. There are other incubators which are thinking in these terms, but there needs to be there are a lot of different pieces which need to come together in order to make an effective AI for climate solution. And different organizations have different takes on this. And I think that these are all valuable, but we haven't seen either enough fields doing this. Like definitely the power sector has been a leader in this space as compared to, say, the steel sector. We need to have more sectors looking at this, and we need to have just more organizations, because fundamentally the more organizations that exist in the space, the more innovation is going to get done.
Thank you.
Okay, we have time for one more question.
If you just want to pass the mic back.
Yeah, just pass it right on back, if you would.
Yeah.
That'd be great.
Hello, thank you again for the talk. My question is about empowering stakeholders and literacy around AI. I'm curious in practical terms how people build literacy, particularly I'm an undergrad student, and how to build skills in visualizing technical processes for non-technical audiences. Because for me, I can already tell from sort of like a more activist perspective that the ability for AI solutions and machine learning solutions to be effective on relevant problems hinges on computer scientists' ability to communicate why they're using which model and what impacts that has on outcomes.
Yeah, this is a great question. So, I mean, the big secret is that all of science hinges on communication. You're not actually going to have any kind of impact with any kind of innovation in science unless you have a way to communicate that. Now, there are different ways to do that. I think that actually developing skills in science communication is really useful if you're planning to have a career in science. And that is regardless of how you are looking to have an impact or what kind of impact. It is also really good for your own career. But I think that this question gets a lot of different ingredients. I would say, zooming out a little bit, I'm not trying to encourage everyone in the room to be thinking about AI and climate change. If you are just now thinking about whether you want to be working in something like pure activism or AI, from a climate impact perspective, maybe activism is the better choice, or certainly policy. There are lots of tools, and think about how your own personal skill set is going to be relevant for climate action. And think about what you enjoy as well, partly because you're going to be most effective doing what you enjoy, and also partly because your own enjoyment matters. So I would think in all of those terms. And in terms of how to develop science communication skills, there are a lot of organizations out there. I don't know, when I was here, I organized some science communication events, but I don't know what still exists. I would definitely look into getting practice in written and oral communication. I would look at the events that exist in science communication in various different ways. And I would just realize that basically any opportunity to engage with other people, especially those who have a different background, is an opportunity to practice engaging with other stakeholders, even if they're friends or family. And that is meaningful in that context, and it is also great preparation. So thinking in all of those terms, does that help answer your question?
And it's a great segue to remind you that this lecture and all of our lecture series will be posted online so others can access it. And by the way, throughout the fall, we'll have workshops. And then in the spring too, and connected with this aspect of AI as it relates to climate change policy action that really didn't come up here. Our last workshop series event in the spring will be on AI on social media and how it pertains to climate disinformation.
Excellent.
And
really
so anyway, I want to thank all of you for joining us today, but please join me in thanking our speaker today for a wonderful overview. Thank you very much. That was terrific.